Hey everyone. So today we are going to be talking about STP, which is standard temperature and pressure, and percent composition. So all STP is, it's just another conversion that we have to learn how to do when I say something like at STP. And then percent composition is we're just trying to figure out if we look at a compound, what percentage of that is made up of, say, of a certain element, how much of that is made of another element. So today you should be well versed with doing conversions involving STP, and finding the percent composition of any compound I give you. So first, let's talk about STP. STP, as I said previously, stands for Standard Temperature and Pressure. Okay, it's just a temperature and pressure that we fit to a certain environment. So the environment is 1 atm and 273 degrees Kelvin, and that way that's just kind of like our base environment to study how gases act. So like I just said, standard temperature is 273 degrees Kelvin, and the standard pressure is 1 atm. Okay, atm is just the pressure you feel from the atmosphere. Right now you are feeling somewhere around 1 atm. You go up higher in the mountains, you feel less than 1 atm. You go below sea level, you feel greater than 1 atm. But anyway, that is not too big of a deal. All you need to know is that whenever I say at STP or at 273 degrees Kelvin and 1 atm, all you need to know is that 1 mole of gas at STP equals 22.4 liters. And that is the main conversion that we care about today. So what I'm going to be doing is I'm going to be giving you, say, a certain amount of gas, like 10 liters, 50 liters, 6 liters, and you'll be converting it to moles. Alright? And that's just dividing by 22.4. And then sometimes I might give you moles and ask for you to convert it to liters, and then you'll be timesing by 22.4. Alright, so that's the conversion we're doing today. Let's go ahead and let's get an example going. So, our first example, I'm going to leave this conversion right here for us. And the first example I'm going to ask is, what is the volume of 3.22 moles of argon gas at STP, at standard temperature and pressure? Whenever you see STP, you're going to be thinking right off the bat that I'm going to be using this conversion right here. Once again, I always start with what I'm given and I try to get to what I want. Remember, volume is the measure of how much space something takes up, and volume is measured in liters. So all we're doing here is trying to go from moles to liters. Luckily, this is at STP, and we know that 1 mole equals 22.4 liters at STP. So we start with what we given, which is 3.22 moles, and all this is a simple conversion. So when I do a conversion, I'm going to do multiplication dot fraction bar. I'll put moles on bottom so they cancel out. And what I'm looking for is volume. So I'll put liters on top. And what I'm going to tell you here is that 1 mole at STP is 22.4 liters. So all we're doing is multiplying by 22.4. You want to go from moles to liters, you multiply by 22.4. So I'll go ahead and I'll do that in my calculator. Actually, I have it written down already, so I'll just say it is 72.13 liters. Okay, that's all STP is. It's pretty simple. It's just one more conversion. It's just when we're dealing with gases and volume. Let's do another one. Say I have, let's go with, I have 100 liters of O2. How many moles is this at STP? Okay. How many moles is this at STP? Well, again, I say STP, so you know at some point you're going to be using our nice conversion of 1 mole equals 22.4 liters. Well, we start with what I'm given, which is 100 liters. And remember, I'm trying to get to moles. So all I'm going to do is multiplication dot fraction bar. I'll put liters on bottom so they cancel out. I'll put moles on top because that's what I want. I have a straight conversion from moles to liters at STP. And that is that 1 mole at STP equals 22.4 liters. So now, if we have liters and we want to get to moles, we just divide by 22.4. So 100 divided by 22.4 is just 4.46 moles of O2. Okay, so that's all we're doing. If you want to go from liters to moles, you divide by 22.4, like we did here. If you want to go from moles to liters, you just multiply by 22.4. But remember, it's got to be at STP, okay? If you see STP, you know at some point you're going to be saying, all right, I got to use 22.4. Now let's do something where we might have to go from grams to liters, okay? Or maybe molecules to liters. So, let's say that I have, let's say that I want to know how many liters are in 100 grams of chlorine gas, which is Cl2, at STP. How many liters are in 100 grams of chlorine gas at STP? Well, STP is here, so I'm going to be using 22.4, right? That's our conversion for us to get from moles to liters. But we have a problem here. I didn't give you moles, right? I gave you grams. Well, what can I do with grams in order to get it to some sort of unit where I could change it to liters? Well, remember, I could go from moles to liters using 22.4, so I need to get grams to moles first. And to do that, we divide by the molar mass. Right now we're going back to our chemical conversions that we did last week. So let's go ahead and let's get this to moles first. So I have 100 grams of Cl2, and the molar mass of Cl2 is 71 grams per mole. I know I'm on the right track because grams cancel out and I'm left with moles. 100 divided by 71 is pretty close to 1.4 moles of Cl2. Okay. So I'm cool there, but I'm not quite done yet, right? Because I want liters. Well, luckily this is at STP, right? So I could just do multiplication dot fraction bar, moles on bottom. I know a straight conversion from moles to liters. For every 1 mole, there's 22, whoops, I did a subscript there, 22.4 liters at STP. So 1.4 times 22.4 is 31.36 liters. Okay. So again, we're just adding one more step. Let's go ahead and do one more, okay? And then we'll move on to percent composition. So, let me ask you this. How many molecules are in 30 liters of helium gas at STP, at that standard temperature and pressure of 273 Kelvin and 1 atm? So I gotta go to molecules now. But I gotta start with what I'm given. Right now, what I am given is 30 liters. Unfortunately, I don't have a straight conversion from liters to molecules, right? The only thing that I know right now that I could change liters to is moles by using 22.4. So let's just start there and see what we can get. liters on top, liters on bottom. The only thing I can change to is moles. Luckily, I'm at STP, so I know that 1 mole is 22.4 liters. And also, just want to reiterate, this is only for gases, okay? If you are dealing with solids or liquids, this doesn't work, okay? This only works with gases. So let's just go ahead and let's do 30 divided by 22.4, and I get something like 1.34 moles of helium gas. And I'm going to move that down here so I have a little bit more room. And remember, our goal now is to get to molecules. And I know a conversion for molecules, right? I know that for every 1 mole of anything I have, it is 6.022 times 10 to the 23rd molecules, or MC for short. Cancel out moles. I'm going to times 1.34 times 6.022, second e to the 23rd, and I get 8.07 times 10 to the 23rd molecules of helium. So now if we know like the volume of a room or the volume of a whole house or a stadium, we can figure out actually how many molecules of gas there are in it. And we'll do something like that later on. Okay, let's move on to our next part of our lesson, which is percent composition. And this one's really easy, guys. Okay, it's percent composition. And let's start with our very friendly compound of H2O. And I might just ask you, what is the percent composition of H2O? What is the percent composition of H2O? That's just pretty much asking you, what is the percentages that make up that compound of H2O? So what percentage of this H2O is hydrogen, and what percentage of this H2O is oxygen? And what we're going to use to figure that out is our molar masses on our periodic table. So what I'm going to do is, the first thing I'm going to do is I'm going to figure out the molar mass of water altogether, which we should know is 18. The molar mass of hydrogen is 1. I got 2 of those. And the molar mass of oxygen is 16. So the molar mass of water is 18 grams per mole. So I'm going to put 18 on bottom. And the first thing I'm going to do is I'm going to go ahead and figure out the percent composition of hydrogen in H2O. So all I'm going to do now is put the molar mass of all the hydrogens on top. Well, what was the molar mass of all the hydrogens in water? 2, right? There's only 2 hydrogens in here. The molar mass of all those hydrogens is 2. So I'm going to take that 2 divided by 18, times it by 100, so I get a percent. And that will tell me what this percentage is of water, which ends up being somewhere around 11, or hydrogen, 11.1%. So this, the percent composition of this is 11.1% hydrogen. Now let's figure out the percent composition of this, that is oxygen. 18 on bottom, right, because that's the molar mass of the whole thing, versus what we want on top, which is just oxygen. And there is only 1 oxygen with a molar mass of 16, which, you know, percentages got to be out of 100, right? So I'll do 16 divided by 18 times 100, just to be sure. It's good. It's 88.9% oxygen. Right, so again, you can just take that out of 100. You could have took 100 minus 11.1, and you would have gotten 88.9. So that's percent composition. All we're doing is we're taking the molar mass of each individual atom and putting it over the total and timesing it by 100. So let's do another one, okay? Let's do what is the percent composition of sulfuric acid, which we should know is H2SO4. So now I want the percent composition of this H2SO4. So that means I'm not just finding the percent composition of 2 elements, I am finding the percent composition of 3 elements: hydrogen, sulfur, and oxygen. So first things first, I'm just going to put a little column here for each one. I'm going to figure out the molar mass of all of this all together. Okay? Hydrogen is 2, because I have 2 hydrogens with 1 each. Sulfur has a molar mass of 32. And oxygen has a molar mass of 16, but since I have 4 of them, that'll be 64. So I should have 2 plus 32 plus 64 will give me a total molar mass of 98 for each of these. Okay, that is the molar mass of H2SO4 on bottom. Let's go ahead and figure out the molar mass of all the hydrogens, right? Hydrogen has a molar mass of 1, but since I have 2 of them, that gives me a total molar mass of 2. I'll times that by 100, and the percent composition of hydrogen and sulfuric acid is 2.04% hydrogen. That makes sense because hydrogen's pretty small and there's only 2 of them in this whole thing. Sulfur. The molar mass of sulfur is 32. I only have 1 sulfur. So now I'm going to do 32 divided by 98 times 100. And I get something like 32.7. Well, let's keep it consistent. I went to the hundredths there. Let's go 32.65%. Here is sulfur. And the last one, oxygen, right? Oxygen is 16, but since I have 4 of them, 4 times 16 is 64. Times 100. I put 65, we don't want that. That will give us 65.31% oxygen. And I look at these and it looks like it adds up to 100%, right? 32 plus 65 is 97, plus 2 is 99, and then the rest of my percentages should give me 1 full percent to give me 100%. So that's percent composition. Let's do one more and then I'm done, okay? What is the percent composition of CH3OH or methanol? So now I'm dealing with carbon, hydrogen, and oxygen, or CHO. Okay, so again, let's figure out the molar mass of this whole thing and put that on bottom. Carbon is 12, hydrogen is 3, oxygen is 16, and that hydrogen by itself is just 1. 15, 32. Okay, so 32 grams per mole is our total. Okay. Carbon makes up just 12 of the total molar mass. Hydrogen makes up, these 3 and that 1, 4 of the total molar mass. And oxygen makes up 16 of the total molar mass. Let's do some calculating here. 12 divided by 32 times 100 is 37.5% carbon. 4 divided by 32 times 100 is 12.5% hydrogen. And 16 divided by 32, you could figure, is 50% oxygen. That's it, people. Okay? So that is percent composition. That is STP. Now we should be able to go from liters to moles, liters to grams, liters to molecules, and vice versa due to STP and knowing that 1 mole at STP equals 22.4 liters. And now we should be able to find the percent composition and figure out how much of each element makes up the total compound. That is it for today, guys. Try out that practice and let me know if you have any questions, and have a great day.